Hello everyone and welcome back. Today we are going to talk about force buoyancy. We are going to discuss what it is, why it exists, and how to find it. Now, to really get the point across, I'm going to introduce this mathematically because along the way it's really going to hammer down one of the very important connections that you need to make. Now, before we continue, it should be noted that you should definitely have a pretty good understanding of the pressure at depth equation and what it means, which was discussed in my last video. Now, as I said, I'm going to introduce this mathematically, so feel free to grab a sheet of paper and follow along, or if you need to, pause the video, let's sink in what I'm talking about, and then continue. So to start, here's our waterline, and I'm going to use this box right here. So this box is underneath the waterline, say in the middle of a swimming pool where the floor is down here. Now, what the box is made of is not important. It could be air, it could be wood, it could be plastic, it could be steel. Whatever it is not important. What is important is the fact that it is displacing water. That something is here and the fluid is around it. Now, I'm going to give the box measurements. We'll say it is 3 meters long, 2 meters wide, 2 meters tall, and the top of the box is 4 meters below the water line. Now, what we're going to do is we're going to find the net force on the box from the fluid around it. Which means, if you remember from my last few videos, there is a force exerted on each side of this box in the direction of the box itself. So, there is a fluid on the right side on the box pushing it to the left. And there is a fluid on the left side of the box pushing the box to the right. Same thing with the forward and back, and same thing with the down and up. Now, the first thing we should note is that if we are trying to find net force, we should first try to find any forces that cancel out. And in this situation, there are some. First of all, the area on this side of the box and the other side of the box here are the same. The average depth is also the same. Since they are the same height top to bottom and front to back, 2 meters, 2 meters, and the center is 5 meters below the waterline, that means that the force to the left and the force to the right are equal. They will cancel out because same fluid, same depth, same area, both are perfectly vertical. Force left, force right, exact same value, they cancel. Therefore, we are not going to worry about these two. The same is true of the force toward the front and the force toward the back. In other words, this surface here and the surface exactly opposite on the other side are both vertical, have the same area, and have the same depth, so those two forces cancel as well. That means we are now left with two forces. The force of this water column pushing down on the box due to the pressure from the fluid, and the force due to pressure from the fluid on the bottom of the box pushing upward. So here is the force downward, and here is the force upward. Now, if you notice, I made the force upward a little larger. We already know this is going to be true because of this value, h, which is going to be the distance from the point we are looking to the water line. And the bottom of the box is going to have a larger h than the top of the box. Let's actually work out the math and take a look at this. So I'm going to start with the force fluid upward on the box. Looking at our pressure equation down here, that force is going to be pressure times area. And the pressure is going to be rho g h. All right, times area. We are still using water, 1,000 kilograms per meter cubed. G is still 9.0 meters per second squared. The height we're going to use is going to be 6 meters because we're talking about the force exerted on the bottom of the box. In other words, the fluid is pushing upward. So 6 meters. And the area is going to be the area of the bottom of the box, which is going to be 3 meters times 2 meters. So this will be 6 meters squared. All right, now that I have the more appropriate units for G, let's take a look at the units. Kilograms cancels. I have meters and meters squared here, which is meters cubed, which will cancel with this meters cubed. Therefore, the only unit left will be newtons. And that means I will have 352,800 newtons upward. All right, now let us take a look at the force downward on the box. So this is the force of the fluid being exerted on top of the box, pushing the box downward. So force fluid down will be again pressure times area, rho GH area, except this time the height will be 4 meters because we're going to the top of the box, not the bottom. And that will give us a force of 235,200 newtons downward. So let's combine these and see what we get. I'll use upward as positive. So 352,800 upward minus the 235,200 newtons downward will give us 117,600 newtons upward. Now, this is going to be a very important number. But before we get into details on that, there's something I'd like to point out in the math. The force fluid we just found came down to this. Rho GH1 times area minus rho GH2 times area, because the height was the only thing that was different. That means I literally could have done this. Instead of finding the individual forces, I could have done rho GH height 1 minus height 2. Now here's why that is important. This 4 meters did not matter. Height 1 was 6 meters, height 2 is 4 meters. 6 minus 4 is 2. I could have made this 20 meters. Height 1 would have been 22 meters. Height 2 would have been 20 meters. The difference would have been 2 meters. I could have made this 100 meters. Height 1 would have been 102 meters. Height 2 would have been 100 meters. The difference would have been 2 meters. It would not matter. It did not matter. For force buoyancy, how deep the object is does not matter. It could be 2 centimeters below the waterline or 1,000 meters below the waterline. Does not matter. The only thing that matters, as I'm about to show you, is how much fluid is displaced. Watch this. Instead of looking at the individual surfaces, I'm going to look at the volume here. So it's length with height, 3 meter length times 2 meter width times 2 meter height will give us 12 meters cubed. So this is the volume displaced. Now I'm going to show you something pretty cool. We're going to take a look at the force earth or force gravitational of the fluid that is displaced by this box. That will be mass of the fluid displaced times G. Look at my density formula again. That would be density of the fluid times volume times G. That would be 1,000 kilograms meters cubed times 12 meters cubed. Notice the meters cubed are already going to cancel. Times 9.8 newtons per kilogram. So, kilograms cancel, meters cubed cancel. Again, I am left with newtons. And if I do this, I get 117,600 newtons. And this will work every single time. We literally just calculated the combination of forces for the fluid on each side of the surface. So the ones that were different were down and up. If you calculate the gravitational force exerted on the fluid that is displaced, force buoyancy will equal that value every single time. And how deep the object is, or how deep that displaced fluid is, does not matter. As I just showed you, this 4 meters did not matter at all because you're getting the difference between the depths. That statement was so important that I'm going to repeat it, and you should probably write this down. Buoyant force is equal to the gravitational force on the fluid displaced, but upward. So, if you're looking for an equation for force buoyancy, here it is. It is the mass of the fluid displaced times G, typically written as density of the fluid times volume of the object times G. In other words, whatever this object is, and it doesn't matter what it is, like I said earlier, it could be wood, it could be glass, it could be steel, doesn't matter. That volume, whatever it is displacing the water. There's no water within that boundary. So you need the volume of the fluid displaced, but the density of the fluid itself, because that is what is exerting the forces. And the direction of this force is against the direction of the gravitational field, so the direction of the force is upward. This is what makes an object float. If you take a ball and drag it underwater and let go, it's going to start floating upward. This is what is doing that. One of the biggest errors is people confusing this because they may give you the density of the object just to see if you put that in here by accident, but you need the density of the fluid. The only time the density of the object may be useful is if you're going for true net force. That means you would need force Earth on the object, which is downward, and force buoyancy, which is upward, and then subtract the two. And one more warning, this is typically just written as rho volume G. So you need to have an understanding of which rho you need, which is the fluid, and which volume you need, which is how much of the fluid is displaced. So let's take a look at a situation where you're actually going to need this. And to do that, we're going to take the same box, only this time the box will be floating. So here's my water line. The box is floating, so some of it is above the water, and I'm going to add some measurements here so we can see how much is actually sticking out of the water. Now the question is going to be, what is the density of the box? Now for starters, we know these forces must be balanced because the box is floating there and it is not moving, no acceleration. Therefore, force Earth on box must equal force buoyancy on box. Just like if this box was sitting on a table, force Earth would equal force normal. So since we know that equivalency, we are literally going to start with that. Force Earth on box equals force buoyancy on box. Now let's break this down. I'm going to do the right side first because we just derived it, and it's in the lower left-hand corner here. Density of the fluid, volume displaced, times G. Now I have volume of the object down here, but that's probably not entirely accurate because the entire object is not underwater. Only part of it is. Because the only part of the volume that you want is the part that is actually displacing water. So I'm going to get rid of this now in the hope that everyone understands that concept. And I'm going to put these values in. Density of water. Volume is going to be 3 meters times 2 meters times 0.6 meters times G. Since I have this written down, I'm just going to throw this down now. 35,280 newtons. Now let's take a look at the force Earth side. Well, we know force Earth equals mg. But since we're looking for the density of the object, I'm going to write this in terms of density instead of mass. And to do that, we can just use our density equation again. That's density of the box, volume of the box, times G. Density of the box is unknown. The volume of the box is 3 meters times 2 meters times 2 meters. In other words, Earth is pulling down on the entire box, not just part of it. Times G. Combining D's, that would be 117.6 Newton meters cubed over kilograms. The last step would be to divide this out. The newtons would cancel. This unit would flip because you're dividing by a fraction, and you would get the density of the box to be 300 kilograms per meter cubed. To do a quick check, anything that is floating should have a density that is less than water, and this box definitely does. On a side note, just to reference an earlier video, to look for the specific gravity, divide the density by the density of the fluid it is in, so the specific gravity would be 0.3. And any specific gravity of a substance that is less than 1 will float in water, or in the fluid that you are referencing it to. So, quick recap. Force buoyancy exists because the pressure on the bottom of the object pushing upward is going to be greater than the pressure exerted on the top of the object pushing downward because the bottom of the object is lower in the water column. It does not matter where in the water column the object is. The bottom of the object is going to be lower in the water column regardless by the same amount each time. So the depth does not matter. What does matter is how much fluid is displaced. Buoyant force is equal to the gravitational force of the fluid displaced, but upward or against the gravitational field. Here is the actual equation for it. Force buoyancy equals density of the fluid displaced times the volume of the fluid displaced. Use whatever subscript makes more sense to you, times G. If the shape is a common geometrical shape, like this cuboid or a sphere, you are expected to know how to get the volume. The volume of a sphere is actually literally written on the AP exam's equation sheet. Any other shape that is unusual, like a person. If you went underwater, you have a volume, you displace fluid. That volume is either typically given to you, or you need to find it by doing one of the equations we just used, but in reverse order, where you are finding a different variable. Typically, you're looking for force buoyancy, but they can give you force buoyancy and you're looking for volume. Basically, once you have the equation down and the equivalency written down, it's just a game of, okay, what am I missing? How can I find it? And lastly, it does not matter if the object is floating. This equation still holds true. The only difference is you only care about the fluid that is actually displaced. You do not care about the volume of the actual object. So the fluid displaced is used for force buoyancy. The volume of the whole object is used for gravitational force if you are using that, like in the problem we just did. All right, so we discussed force buoyancy, why it exists, and how to get it. Did a little practice. I hope this helps everyone out. I think I'll end it here. This is Mr. M, signing off.